So this was a peak moment of my career, but it left us with a question: how do we cope with these problems? We still have to schedule our factories and our schools. We still have to ship cement from factories to the battlefront and so forth. We still have to optimize production in different ways. And not only that, there are many problems in pure mathematics that we would like to attack from this point of view. So how is it that the world doesn't grind to a halt? How is it that we can still dispatch taxi cabs and pack the suitcases into the trunk of the car? And partly it's because some of these are fairly small instances, but it's more than that. We seem to be able to do well on quite huge ones as well, even though the problems are NP-complete. So what is a possible methodology for demonstrating that all is not lost, that we can really do well? In practice, people seem to muddle through. They can take some big, very complicated problem like scheduling the classes at a school, and they'll somehow be able to play around and eventually get a solution that satisfies almost all of the constraints that are posed. So the standard way that people in theoretical computer science attack this is to formulate the problem as an optimization problem, to ask not only is there a solution or isn't there a solution, but to in some way attach a cost to different possible solutions. A good example would be the traveling salesman problem, where you have distances between cities and you want to make a tour that minimizes the total distance. So people started proving theorems of the form, here's a polynomial time algorithm that solves problem X within 10% of the optimum. This led to a great extension of the theory of combinatorial optimization that pioneers like George Dantzig and Fulkerson and Edmonds and other people had developed, using methods based, in many cases, based on linear programming to get these approximations. Unfortunately, practitioners were not terribly satisfied with these solutions, with these bounds. So, for example, a famous worker in computational biology once said to me, why do I care that they can prove it within a factor of 10 or log n in the worst case when I'm solving instances every day within 1% of optimal? So in short, it has turned out that in most cases, the bounds that one can prove about the degree of approximability using a polynomial time algorithm are a bit too pessimistic to really satisfy practitioners. So when I came off my administrative post and had a little bit of time to think, I began to ask myself, how can we bridge the gap? How can we get some constructive results to demonstrate that all is not lost with these NP-complete problems? And it occurred to me that maybe the thing to do was to show that some of these problems were efficiently solvable on the average. So I began to delve into average case complexity. What do we mean by solving a problem on the average? So you have to define some probability space of problem instances. For example, if you're looking at a problem on graphs, you might assume that all the graphs with a given number of vertices and edges are equally likely. It's a very simplistic assumption. Or if you're dealing with a problem where the data in the problem consists of the numbers in a matrix, you might assume that these numbers are drawn independently for some simple distribution. And indeed, if you're willing to make assumptions like this, you can prove nice theorems. You can prove that it's easy to for example, to find what's called a Hamiltonian circuit in a graph, a tour that visits all the cities without repetition. And many of these problems become easy. You can show that the traveling salesman problem can be solved with very small relative error. And so I reveled in this and had a great time proving results of this kind for a few years in the mid to late 70s. The reception for this kind of work by the community was at best mixed because the simple probability distributions that we were assuming didn't strike people as being particularly descriptive of the kinds of problems that would come up in practice.
Perhaps the intellectual tradition of computer science has been to be agnostic about where the inputs come from.
Yes, yes. You'd like something that works for all inputs, and that was not being provided by this probabilistic analysis. So I had a great time with it, but it was not necessarily a landmark achievement in terms of the progress of the field. However, a related direction became very prominent. In the kind of probabilistic analysis that I was engaged in, the probability is in the generation of the input. So you're assuming that the input is a random graph or a random matrix or something of that nature. There's another way to inject probability, which is to assume that the input can be any graph, any matrix, any data object, but that the algorithm is allowed to generate random numbers, or allowed to have a source of random numbers, random zeros and ones, for example. In a 1976 paper presented at a conference at Carnegie Mellon University, Michael Rabin, the hero with whom I had commuted to IBM back in those days, again inspired me and the whole community by giving some beautiful examples of algorithms which depended on a source of random numbers and could solve problems that we didn't know how to solve without randomization. And he gave two very striking examples. One of them is the problem of finding the closest pair of points in d-dimensional space without exhaustively looking at all pairs. And the other one was testing whether a number is prime, whether a number has no divisors except itself and 1. So Rabin, building on some earlier work by Gary Miller, who was a student at Berkeley at the time, gave a randomized polynomial time algorithm for testing whether a number is prime. The algorithm depends on random coin tosses, random bits. So it generates random tests that can be applied to the given number. If any of these tests fail, then you have a demonstration that the number is not prime. But if these random tests succeed, then you're left in doubt as to whether the number is prime or not.
But tiny doubt.
But very small doubt, because every time you generate a new random test, if the number is not prime, you'll have at least a 50% chance of showing that it's not prime. So if you apply a series of such tests, the chance that a number that's not prime would survive and remain in doubt would become vanishingly small. So in practice, this kind of randomized algorithm is really quite useful and quite valuable. The first polynomial time randomized algorithm for primality was actually due to the mathematicians Solovay and Strassen. But the version that was due to Miller and Rabin somehow, through the force of Michael Rabin's character in part, led to a revolution in the way we think about algorithms.